Hello AP students. Before we begin, please make sure you have the following things in front of you. You need the packet of the PowerPoint slides that have been printed out for you. You need your impulse and momentum practice problems. And you need your notes open. Okay, so we're going to be analyzing the motion of systems from a different perspective today, called the center of mass perspective. To find a system center of mass, you're going to be weighting the mass based on the position of those masses away from some arbitrary origin. And so this is the equation for center of mass, where x is position, like always. So this is the position of the center of mass. And it's the summation of the mass times the individual position. So here's object 1, here's object 2, and so on and so forth. So mass times position, plus mass times position, and so on and so forth, all divided by the total mass in the system, m1 plus m2, and so on and so forth. So you can put this in your notes. You're also going to box it in and put it as a new equation on your list of new equations, where xcm stands for the position of the center of mass. And now in your PowerPoint slides, you're going to be looking at the first one there, which correlates to problem number 5 in your packet of problems. So you want to have both those in front of you, PowerPoint slides as well as number 5. This is our first conservation of momentum problem, where the boy and the girl were standing on the ice, and then they explode away from each other. The position of the center of mass right now, I'm going to say, is equal to 0. So this blue line represents their arbitrary starting point for the position of the center of mass. And when we solved the problem, of course, we found that when they exploded away from each other, the boy went off at 2 meters per second to the right, and the girl went off at 4 meters per second to the left. And so we're going to be tracking this second by second. So if you look at the next slide on your packet of PowerPoint slides, we're now at time equals 1 second. And so she moved off 4 meters per second to the left, so at 1 second she moved 4 meters. We're calling left negative. And he moved off at 2 meters per second to the right, so we're calling right positive. He moved 2 meters in 1 second. If we calculate the position of the center of mass, it's his mass, 80 kilograms, times his position, positive 2, plus her mass, 40 kilograms, times her position, negative 4, divided by their total mass. And you can see that these actually cancel out to a net overall position of 0. So the blue line has not moved. If we take it to the next second, at 2 seconds, she's moved another 4 meters to the left, so she's now at negative 8. He was another 2 meters to the right, he's at positive 4. We put the numbers into the position of center of mass equation. You notice that everything cancels out. You may want to take a second now to pause the video and just confirm some of these calculations for either this one or the 1 second position. And now you should be able to confirm that certainly the position of the center of mass again has not changed. So here it is at 3 seconds. Again, you can put the numbers in. She's at negative 12. He's at positive 6. Put the numbers in. They cancel out to 0. At 4 seconds, again, she's at negative 16. He's at positive 8. And the positions cancel out to 0. And so you can see that the blue line has not moved. Now notice that the system of the boy and the girl started at rest. The position of the center of mass also seems to have been at rest the entire time. It's almost like there's an object there at the position of the center of mass, and since nothing has happened, the position hasn't changed. It stays at rest. So we can say it like this: in the absence of external forces, the motion of the center of mass of a system remains unchanged. This sounds awfully familiar. It kind of sounds like Newton's first law. And this is Newton's first law for systems. So please make sure, of course, you are copying this down into your notes. You can pause the video to do so. Now, this example we just looked at in problem number 5 dealt with a system that was at rest. It started at rest, and as the objects moved away from each other, the center of mass positions remained at rest. Well, now let's turn to problem number 7. So here's number 7. This was little brother approaching chaperone son. Chaperone son's at rest here. Little brother's approaching at 10 meters per second. And they're on a number line here. And I just arbitrarily decided that this position here is the 0 position. And chaperone son starts at negative 10. And little brother starts 30 meters away, moving in at 10 meters per second. So if this is our 0 position for the just our arbitrary number line, everything's measured away from that, and we calculate the center of mass position. Here is little brother, 30 kilograms at 30 meters, plus chaperone son, 50 kilograms at negative 10, divided by the total mass of 80 kilograms. And so here's the position of the center of mass. You can feel free to pause the video, do the calculation. You'll prove to yourself the position of the center of mass is at positive 5. And so you're going to put an x at that position. So here's the position of the center of mass at this moment when time equals 0. Again, we're going to look at it second by second. So here's the next slide. At 1 second, remember, he's moving at 10 meters per second. He's advanced 10 meters into the left, so now he's at 20 meters. Chaperone son still at 0. This is still the blue line representing x equals 0. You put the numbers in. Now, when you calculate everything, the center of mass is at a position of 1.25. It used to be at 5 meters, now it's at 1.25. So here we're calculating the velocity of the center of mass. In 1 second, it changed position from 5 meters to 1.25 meters, final minus initial. And you see that the velocity of the center of mass is negative 3.75 meters per second. It used to be here at 5 meters. It's now moved 3.75 meters to the left in 1 second. At the 2 second mark, little brother's advanced another 10 meters. He's now at a position of 10 meters. Put the numbers into the position calculation, and now the center of mass is at negative 2.5 meters. Again, feel free to pause the video and calculate that for yourself. Here again, we calculate the velocity of the center of mass. It used to be at 1.25 meters, now it's at negative 2.5 meters, and you see it's traveled another 3.75 meters to the left. Well, that's interesting, because before the velocity was negative 3.75, now the velocity is negative 3.75 meters per second again. We advance another second. Little brother happens to be at the 0 position. Put the numbers in. The position of the center of mass is at negative 6.25 meters, the position of the x here. You put the velocity numbers in, and lo and behold, the position of the center of mass has moved another 3.75 meters to the left in 1 second. So we see that the velocity of the center of mass, even though there's no actual object at the position of the x, the center of mass position has moved a consistent 3.75 meters to the left every second. Here they are colliding. They're at the same position at negative 10 meters, and we plug it into the value here for x of the position of the center of mass, and we get that they're at negative 10. They're at the same position, which makes perfect sense. And lo and behold, it's traveled another 3.75 meters to the left in 1 second. So we see this consistent velocity for the center of mass. It's always moving to the left at 3.75 meters per second as little brother approaches chaperone's son. Let's see what happens next, because the next second, they separate. At time equals 6 seconds. Now, of course, we're in an after situation. The little brother rebounded 2.5 meters per second to the right. Chaperone's son goes off at 7.5 meters per second to the left. So in 1 second, chaperone's son moves from 10 to negative 17.5. In 1 second, little brother moves from 10 to negative 7.5, 2.5 meters per second to the right. Here's our equation for the center of mass position. The center of mass is at negative 13.75. It still moves to the left. And look at this. Here's the velocity equation. It moved from negative 10 to negative 13.75. It still moved negative 3.75 meters per second. And so you can see throughout this entire interaction, the center of mass continues to move to the left at 3.75 meters per second as if there's an actual object there moving at a consistent velocity at 3.75 meters per second to the left. So our Newton's first law still works. It's as if there's an object at the center of mass. The motion of that quote-unquote object remains unchanged. It was constantly moving 3.75 meters per second to the left. Again, as long as there's no net external force, as remember is what happens here on the frictionless system of ice. We can then also say this is sort of like Newton's second law. The sum of external forces on a system determines the acceleration of the center of mass of the system. It's like sigma F equals ma. This is Newton's second law for systems. Feel free again to pause the video and write this down. So these laws act in conjunction. As long as there's no net external force, the net external force is 0. That means there's going to be 0 acceleration for the system. And so the system maintains its motion. In problem 5, the system started at rest, and the position of the center mass remained at rest. In problem 7, the center mass is always moving at 3.75 meters per second to the left. It continues to move at 3.75 meters per second to the left. No acceleration for the system. We can then extend this to a system if there were actually a net external force. Right now on this ice, there's no net external force, but if there were, for example, a slanted system, so that gravity was acting on the whole system, and the whole system would accelerate down the incline, you could still apply Newton's second law to the system to the point that the net external force would cause an acceleration to the center of mass of the system. Let's look at problem 7 again from a completely different perspective. So here is what it probably looks like in your problem set, where here's the before situation and here's the after situation as they rebound away from each other. And now I want you to take the point of view of chaperone's son. So if you imagine you're chaperone's son, you're watching little brother coming at you. Clearly he's coming at you at 10 meters per second. So imagine he's coming at you, he's approaching you 10 meters per second. And now let's look what happens afterwards. After the collision happens, now you are moving backwards at 7.5 meters per second, while chaperone's little brother moves away from you at 2.5 meters per second. So imagine again, you're chaperone's son. And from your perspective, how fast is little brother moving away from you? Take a second, pause the video, think about it. You should be able to see that in the beginning, little brother's approaching chaperone's son at 10 meters per second to the left. That's what we call the relative velocity. Or if you're chaperone's son, he's approaching you at 10 meters per second. A little bit of thought shows that these velocities being in opposite directions show the relative velocity is 10 meters per second, but now to the right. They move apart at 10 meters per second. Or if you're chaperone's son, little brother's moving away from you at a relative velocity of 10 meters per second. Well, look what happens. The relative velocity is the same magnitude, but in opposite directions. This happens only for this particular type of collision. And hopefully you should be able to see, by looking at the results for the kinetic energy, the kinetic energy is conserved in this situation. This is an elastic collision. And so in your notes, you're going to write this, that for elastic collisions only, we have this very interesting result, that the relative velocity approaching equals the opposite of the relative velocity receding. Here, v1 minus v2 represents the relative velocity of the two objects, in this case 10 meters per second to the left. Here, v1 prime minus v2 prime represents the relative velocity afterwards, 10 meters per second to the right, and so it has the same magnitude, but here's that negative sign, opposite direction. This can only be used for elastic collisions, and just gives you one more equation when you're solving problems. So if you know a problem involves an elastic collision, and you've already done the conservation of momentum equation, you can then do the conservation of energy equation, and this provides one more way of thinking about it that would help you solve a system of equations involving an elastic collision. This equation is not the sort of thing we're going to be doing very often, so notice I'm not boxing it in here, and I don't require that you box it in either. If you wanted to add it to your list, you certainly can, but it's the sort of thing that really is just if you're doing a really complicated problem, you need one more equation to solve, this is the one you would go to for an elastic collision.